Hello, and welcome back to Electrochemical Engineering. Hello, and welcome back to Electrochemical Engineering. Today I'm going to talk about battery cells and pack design. Hello, and welcome back to Electrochemical Engineering. Today I'm going to continue our discussion of battery cells and pack design. Here, highlighted in this slide, hello, and welcome back to Electrochemical Engineering. Today I'm going to continue our discussion of battery cells and pack design. Here I've highlighted a paper from Tarascon and Armand, Nature, from about 20 years ago, showing various types of typical battery cell designs. Here's the cylindrical jelly roll cell that we've been talking about, prismatic cell, a coin cell, and a pouch cell. We'll go through some of these and other types of cells in this lecture. Let's talk about the materials and construction of a typical 18650 battery. Remember, that's an 18 millimeter diameter and 65 millimeter length cylindrical cell. Typically, it's made of a copper foil for the negative current collector. That's because copper doesn't lithiate at the same potentials that graphite does, so it stays a robust current collector. You'd like to use something lighter than copper, like aluminum foil, but aluminum is not stable at the potentials of the negative electrode, which is close to lithium plus potential. Graphite or graphite silicon composites are typically used for the negative electrode material. That's because graphite intercalates lithium ions well, and those lithiums are formally lithium 0 in that graphite at the lithium negative electrode. There's a separator, which is porous, microporous, typically polymeric or cellulosic. There's a separator, which is typically microporous, made of polymer. And then the positive electrode is a metal oxide. We mentioned several different types of metal oxides in the battery science. And the positive electrode is a metal oxide, and we measure, and the positive electrode is a metal oxide, and we mentioned several different metal oxide chemistries like LFP, lithium iron phosphide, or LCO, lithium cobalt oxide, in the battery chapter previously. Aluminum foil is used for the positive current collector because aluminum is very light and it's stable at the potentials where the positive electrode operates. We also have a non-aqueous water-free electrolyte. The basic approach to building a battery like this is you deposit the active material. The active material is going to be the graphite and the metal oxide. You put these materials on the foil current collectors as long sheets. You do that in sort of a roll process. You then cut them into rectangles and stack or roll them into a cylinder. So here's a diagram from this website that illustrates the various steps that go into actually putting together a lithium-ion 18650 cell. So you have your active materials. You make a slurry, carbon plus binder. Binder might be a polymer like PVDF, polyvinyl difluoridine. The binder might be a polymer like PVDF or polyvinylidene. The binder might be a polymer like PVDF, polyvinylidene difluoride. At the cathode material, you'll also have those. At the cathode material, you also have your lithiated oxides with a binder and a slurry. You mix those, and then you coat them on the foil, usually with a slot die or other sort of mechanical coating process. You may compress them. Calendaring is a process by which things are compressed in a controlled way. We take these coated foils and they get compressed, usually by a process called calendaring, where they're fed between two rollers to go from the initial thickness to a compressed thickness. This has a big effect on the microstructure, the porosity of the electrode. So this is a process that needs to be very highly controlled. You pass those foils through a long oven to remove solvent that's used to prepare the slurry and the ink. And then you'll go through a slitting process. And then we'll go through a slitting process. And then we'll go through a slitting process whereby the large coated sheets are sliced into smaller segments that can be rolled up to make the jelly roll. You then take these pieces of anode, coated cathode, and the separator. And for the cylindrical cell, you wind them together. So you take these three pieces as a stack and you wind them in a controlled way. You'll use clamps to connect the electrodes and then insert them into the case. For a prismatic cell, these are made by stacking the electrodes, but the process is similar. You need to weld the case closed. You need to make electrical connections, also connections to vents and any safety devices. It then goes in a dry room where it's vacuum heat dried and then vacuum filled with an electrolyte. So that's where you remove the gas from the pores of the. So that's where you remove first the gas that's filling the pores of your anode and cathode. Remember, you've assembled this whole thing dry. And then you need to inject the electrolyte, and the electrolyte will fill those pores because there's no air in there to prevent the electrolyte from getting in there. You then seal the case and go through the rest of the processes. We'll just emphasize here that the tabs of each current collector, the positive or negative one, must be welded together to connect them. And then you would collect the positive at one end of the battery and the negative at the other end. Also, typically there's a SEI formation step in many batteries, and you might go through a prescribed cycling process to form a stable SEI in the factory before you ship the battery. This is very typical for lithium-ion batteries. A lead-acid battery is a little bit different. This is the sort of interior of a 12-volt lead-acid car battery. What you see is a series of cells. There's 6 of them. Each cell generates 2 volts. And there's plastic separators between each cell. And in a given cell, you can see alternating positive and negative lead plates. And one of those lead plates is coated with lead oxide in the charged state. And one of those plates is coated with lead oxide in the charged state. The electrolytes is sulfuric acid. There's typically multiple plates that are hooked up in parallel, both multiple negative and positive plates interleaved, and we'll show this in a couple slides. That's used to increase the power, so you have higher surface area on your battery to get a larger power. So let's talk a little bit now about electrode and cell design for rate or for high power applications. So for a given cell capacity, amount of charge it can store, the current or the current density are essentially inversely proportional to the time of discharge. So if you discharge your cell fast, you can get a large current, but if you discharge the cell slow, you can only do that with a slow current. So if I want a large cell voltage, then the discharge time must be very slow. So if you have a short discharge, of course, you need a high rate capability. So for short discharge, we of course need high rate capability, power batteries. Where for long discharge, we have low rate capability, energy batteries, batteries that are designed to store large amounts of energy and discharge them at slow rates, relative to batteries that are designed to provide high amounts of power, but perhaps for not that long. Why would you need a high power battery? For example, starting a car. So let's take an example from Fuller and Harb of a battery redesign to get high power and ask the question of how does the cell design influence the power? So let's imagine we wanted to take a deep cycle cell designed for high capacity, lead acid cell, and make it an SLI battery. That's a starting lightning ignition battery, something that has very high power. So Fuller and Harb goes through this example. They say, well, imagine you have a battery process that gives you a 1700 amp hour battery, and you want actually only a 60 amp hour SLI battery. But you want to get the power up substantially. So we can calculate the resistance of the SLI battery. This is going to be a lumped internal resistance. So these are all the various resistances that contribute to the voltage loss in a battery. So it includes ohmic, transport, kinetic, all those types of losses. We're just going to model the battery as a single resistor. We can take the resistance of the deep cycle cell and we can simply scale it linearly via the change in capacity and going from the deep cycle to the starting lighting ignition. And we can scale it so we can again take the resistance. So we can now take the internal resistance of our deep cycle battery. Remember, the internal resistance is just a parameter that describes how the voltage loss due to all the processes happening inside of a battery are related Now we can take the internal resistance for the deep cycle cell. Remember, the internal resistance tells us how easy it is. Now we can take the internal resistance for the deep cycle cell. Remember the returnal. Now we can take the internal resistance for the deep cycle cell. Remember, the internal resistance is a summed resistance, a one-factor representation of the summed resistance of all the various processes that lead to overpotentials in a battery. We can say, well, if we want to estimate the internal resistance of this smaller battery, we know that going from a large battery to a small battery, we will decrease the area of the electrodes. So we can make the assumption that the resistances will scale with area, and if the capacities are also scaling linearly, with area, then we can say the resistance, the internal resistance of our SLI battery, is just that of the original deep cycle battery times the ratio of the two capacities. So the internal resistance would go up here from 0.4 to 11.3 milliohms. By scaling the battery from 1700 amp hours to a much smaller 60 amp hours. We can estimate the mass of our smaller SLI battery just by taking the original mass and again multiplying it by that ratio, so the mass is going to go down substantially. Now, one might want to then estimate how much amperage can we pull out of our scaled deep cycle cell. So the amperage here, this is called CCA, or cold cranking amps. This is important if you're going to start a car. And you might say, well, we want to make sure we can pull at least 7.2 volts out of our battery. We have 12 volts open circuit, but of course we're going to lose some voltage due to the internal resistive losses. So here, 2 volts, that's the voltage of an individual cell in the lead acid battery. And we're going to subtract the current through each cell times the internal resistance. And if we know that we need 7.2 volts for 6 cells, that means we need 1.2 volts for 1 cell. So if you then calculate, given I, if you calculate what is I when R internal equals 11.3 milliohms, like we calculated on the previous slide, you find that the maximum current you can get out is only about 71 amps. And in this particular example, Fuller and Harb make the point that this is actually 8 times smaller than what the desired value is for this application. So what this is telling you, it's sort of obvious, is if you take a battery designed for deep cycle, high capacity, slow discharge, and you just make it smaller, you're never going to get the high amperage out. And you make it smaller because you don't need capacity for a starting application. That battery is not going to be able to provide you the power you need for that application. So how do you go around this? Well, the obvious answer is you can change the electrode design to increase the power at a constant capacity. So imagine I have a 12-volt deep discharge battery. This is something designed for running for a long time at a lower current. And there's 6 cells in series. So here's a cell here. Okay, here's a separator. So here's one cell here. Positive, negative, a separator in the middle, an electrolyte. Here's a plastic spacer and another cell, and a plastic spacer and another cell. And of course, these are wired back to back to back to lead to my 12-volt battery across the positive and negative terminal. So here's the pair of thick plates or thick electrodes. So there's a lot of active material on each one of these electrodes. Now, I could take the exact same volume of a battery, and instead of making just 2 big plates in each cell compartment, so again, here's the spacers between the cells, here's a cell compartment, I can replace that with sets of plates. So now I have a wire going to 1, 2, 3, 4 negative plates, and 1, 2, 3, 4 positive plates. So essentially what I've done by interleaving the plates in this way and also connecting them in this way is essentially increase the area of interaction between the plates by a factor of 4, because now I have 4 times the area than I did before. So what I have done now by interleaving these plates is I have dramatically increased the area. So here I had an interfacial area this much between the two plates. So this is where all the current must flow to go from the positive to negative electrode, the ionic current. But here I now have 1, 2, 3, 4, 5, 6, 7 times as much interfacial area for the current to flow between a positive and negative plate. So this will give me much higher power for the same volume. In principle, if there was no ancillary weight due to the inactive cores of these lead plates, this would have actually the same capacity as well, but of course we have to use some of that volume for extra current collector, the sort of lead in the middle of these plates that is so that's how we think about controlling the electrode architecture within a cell to increase the rate capability, the power capability of a given battery chemistry. Here's some more details on cell construction. Here's a prismatic cell. We'll break that open in a second and show you what's inside. Typically there's a relief valve and 2 terminals. It's prismatic in shape. Here is a typical spiral wound cell. This is the type we've been talking about. There's an inner and you can see on the zoom in here, you can see the repeating copper foil negative electrode coated on both sides with our carbon, separator, positive electrode coated on both sides with our metal oxide with aluminum foil in the middle. All these ends have to be tabbed together. So typically the edges of these materials are welded at some point to provide a low resistance path to collect the current. This diagram is also showing what's called a burst disc. That's a fail-safe in case gas pressure builds up inside here. And insulation between the positive terminal, which is making contact to this wire here, and the negative terminal, which is making contact to the negative tabs via the outer case of the shell. So here's a break. So here's some schematics showing again the cylindrical cell, the prismatic cell, which is sort of wound and then squished. The coin cell, which many of you have made in the lab, typically just has one separator between the two active components, and a pouch cell, which can have a number of layers. And here D, the pouch cell, which consists of alternating layers that can be repeated multiple times to form the battery cell. Here's actually a CT scan of a commercial pouch cell that I found in the literature, and you can really see how the tabbing works here, connecting all the, for example, positive electrodes and negative electrodes together, and how they're stacked and interleaved, coated. Here's the coated electrodes, and here's the separators inside the cell. This is all surrounded by a bag, and these can be quite lightweight compared to the metal can cells and have very flexible form factors as opposed to being cylindrical. Let's now talk about charging of batteries and performance. So overcharging is a term that refers to passing more coulombs than are required to fully charge the cell. This can be bad if it damages the cell. Sometimes it's done necessarily because of low coulombic efficiency. The charge coefficient is the coulombs passed to fully recharge divided by the coulombs drawn during discharge. And this is equal to 1 over the coulombic efficiency. This is called the charge coefficient. You can typically charge a battery at either constant current, CC, or constant voltage. CC charging continues at a constant rate until a specified voltage is reached, whereas constant voltage, you hold the potential of the cell constant and allow the current to vary. So it will start at the beginning charging very fast as the cell voltage is far from the fully charged voltage and you're holding it at a large voltage. And then it will slow down as the battery approaches full charge. Or you could, in principle, do some combination of these depending on how complicated your battery management system is. For example, here, CCCV, the two methods are combined. You charge at a constant current until some max voltage is reached. So this is an example here, charging at a constant current as a function of time until some voltage here until some cutoff voltage is reached, and then you switch to constant potential, which is the final charge potential you want to be at, and you let the current naturally decay. This prevents you from overcharging your battery. You can also do pulse charging, where you charge at high currents and then rest. Or float charge is where you have a charged battery that you basically apply a very small current to maintain a full state of charge. Even though there might be some self-discharge reactions going on, you continually add a small current back to your battery. For example, in your car, the alternator is constantly charging your lead-acid battery. We can use internal resistance to characterize a battery. One very common test, and it's related to battery impedance, is called the pulse power test. So after a rest, here's time, you're resting, not applying any current. You apply two short current pulses, one in the charge direction, one in the discharge direction. So we're starting with a battery that has some charge in it. And we're going to apply our current pulse, 1, which is going to be to further charge the battery. And we're going to apply our current, and we're going to apply our first current pulse, which is going to be to discharge the battery. And I know I'm discharging the battery because it's drawing the voltage down. And there's a specific shape to this voltage profile that's very important as I turn the current on and off. When I turn the current on, there's an immediate change in the voltage. And then there's a slow decrease in the voltage as I discharge my battery. When I then turn the current back off again, that voltage decays to close to the initial voltage, but not all the way. The instantaneous change in voltage is related to the ohmic resistance. So this is I times R ohmic, because the ohmic resistance responds very fast. Whereas the slow part is typically assigned to activation and where this slow part is typically assigned to activation and concentration over potentials. So the total resistance of the cell is just estimated by delta V over delta I, so it's VT0. minus VT1 here. And that includes, of course, all the ohmic activation and concentration resistances. And I showed you how we can take the very fast component and assign that to the ohmic resistance. We can also estimate the cell voltage, assuming the cell resistance is constant and voltage losses vary linearly with current, which is a reasonable assumption. We can also estimate the cell voltage with this cell resistance that we measured in a pulse power test as a function of the current if we assume that the voltage losses vary linearly with current. And this is probably a good assumption over some limited current range. So the cell voltage is just the open circuit voltage minus the IR losses. And now this is the total resistance of the cell from our example pulse power test. Remember that the power of the cell is just I times V cell. So we can write the power as I times V cell, and V cell is just VOC minus the IR loss. We expand those terms, and you get this expression, which looks like this curve here. And the maximum power is found at the point here where dDi goes to 0. And the max power here is found at the top of this curve. Here's the maximum power, where this function dP di goes to 0. So we can take the first derivative with respect to I, set it to 0, and solve for the current that yields the maximum power out of the battery. So the current at maximum power is then VOC over 2 times the resistance of the cell. And the power then at maximum voltage is just the current at maximum. Then the power at I max is just equal to I max times VI max. And VI max is simply VOC minus I max R. And that's how we get that expression there. Because I can plug in here again for I max. So V I max just equals VOC minus I max VOC C over 2R cell D times R cell D. Which just equals VOC over 2. So we can take that, and this is the result of the fact that the voltage loss is linear with the current. We plug it back into this expression, and you get this expression for Pmax. The state of health of a battery is the ability of a cell to meet specified performance ratings. And so this is just typically some ratio between the present capability and design capability. And so that might be for various battery parameters that you care about. To monitor this, you typically have what's called a battery management system. It monitors and controls the current flow in and out of battery cells. It's sort of like a fuel gauge for coulombs. It's actually a chip connected to the battery that controls the charge algorithms, controls how much charge is put in, measures how much charge is put out, and reports the state of health or the state of charge for a given battery. Manufacturers can even input code into the chip to prevent other batteries from working in the system, to give info on the battery life based on a number of cycles. You can think about your laptop, which is able to predict how much power is left, how much longer you can run your laptop. And the battery management system keeps track of the state of health of your laptop battery. They can also be programmed to prevent thermal runaway and overcharging, for example. One thing to think about in a battery is a collection of cells. And ideally, all the cells are identical, so you know exactly how to engineer your battery as a collection of those cells. But what if one cell in a battery has a lower coulombic efficiency than the other cells? That means what if it doesn't charge as effectively and some of the charge is wasted due to side reactions? Cells with lower coulombic efficiency will reach 0% charge before the other cells, and this can lead to damage of the cell or battery, especially depending on how the batteries are wired together. So let's look at an example. This is illustration 8.3 from your book. Imagine you're cycling a battery. This is a nickel cadmium battery. You're cycled between 30 and 80% state of charge. Now, if the nominal current efficiency for charging is 80%, that means that's what the manufacturer has provided and what's the spec. But there's a weak cell that has a coulombic efficiency of only 70%. What happens to the state of charge of the weak cell with cycling? Well, you might start at 80%. You discharge to 30%. Now, when you go back to charge it, all the other cells get back to 80%, but you only get to 74% because the coulombic efficiency for the weak cell is lower. Then when you discharge it again, you pull out that same 50%, going from 80 to 30, now 74 to 24. All the other cells are going down to 30, but this particular cell is going to 24. And if you repeat that, you can see that eventually the cell fails. It goes down to very low states of charge, and that can actually damage the battery and in fact consume power if you're trying to extract charge from a battery cell in series with others, and that cell doesn't have any charge left to give. So for a string of cells in series, remember that the current is passing through all the cells in series. So in fact, it's the smallest cell, the weakest cell, is going to limit the usable capacity of the battery. So you really need to balance the cells in a string. And you want to balance those cells to avoid cases like the illustration of 8.3. One thing you can do is something called passive balancing. You can actually take that energy and have it dissipated in a shunt resistor for cells with high state of charge to bring up the cell with a lower state of charge without overcharging. And you can see here an example of passive balancing where you have a series of cells. They're connected in series in a string. And this circuit here, these resistors, these capacitors that separate the two sides of the cell, and this diode, which can be switched on and off by a controller hooked up to your battery management software. The battery management software can measure the potential of each cell independently. And when one cell is charging too much because another cell is too slow to charge, it can turn on this switch and dissipate some of the energy across these resistors, generating heat to prevent that cell from overcharging. This is called a passive system because essentially the energy which goes into charging is wasted. There's more complicated systems called active balancing systems where the energy is actually moved from a cell with a high state of charge to a low state of charge by the battery management system. This gives you greater energy efficiency than passive balancing, but is a lot more complicated because you have to have a circuit that allows you to do that, and your controller needs to be able to switch and move energy from one cell to the other as the full state of charge approaches. And it needs to be able to move energy from one cell to another as one cell approaches fully charged before the other. The state of charge is a known condition. It's a function of time. So the state of charge is the charge state at some given time plus the integral of how much current you pass through the cell to charge or discharge it over time divided by the total capacity. This is, of course, just Q in or Q out, the charge you're putting in or out of the cell divided by what the capacity is at 100% state of charge. Okay, finally, let's talk about thermal management. The rate of heat generation is proportional to the current in a battery, and therefore the C rate. High C rates mean you charge and discharge a cell very fast. Looking at a cylindrical cell, a sheet wound around a shaft which has some radius, call that Ri, and it has a final radius of the winding R0 here. And if you want to know the temperature of a battery, you have to solve heat transfer equation. It's a differential equation, which is similar to other differential equations we've looked at in electrochemistry. We need to know the thermal conductivity. We need to know the rate of heat generation. That's what this term is, Q dot. And the temperature of the battery will respond based on this differential equation. And this differential equation, of course, describes the diffusion of heat in a medium. You can go through this in Fuller and Harb. He derives it in these very specific radial coordinates, or at least gives the answer for how the temperature in a battery will change given a set of parameters. So here's an example of different charging rates as a function of distance from the center of the battery, the temperature profile. And you can see there can be fairly large differences in temperature, several degrees, depending on the rate of charge or discharge. In fact, if you go charge too fast, the battery could heat up so much that it could explode and catch on fire. Also note that energy goes to heat generation. So the more heat generated, the higher the thermal gradients, the less efficient your charge and discharge process is. Now, the operating temperature of a cell is determined by both heat generation and heat removal. When they're equal, of course, the temperature reaches a steady state. If heat generation is bigger than heat dissipation, heat continues to raise with time, and eventually the battery will overheat, and that leads to a fire. This can be thermal runaway. This can be this type of thermal runaway can happen, for example, if the battery is on float charge, where you're applying a small constant current, or current is going to gas evolution. And then as the current goes up, so of course the operating temperature of the cell is determined by both heat generation and heat removal. If they're equal, temperature comes to a steady state. If one is bigger than the other, for example, heat generation is bigger than heat dissipation, then the temperature slowly raises with time, and this can lead to a fire. Call this thermal runaway. On one example, if you're on float charge, say at a constant voltage, or some of your current is going to gas evolution, as the current passes, it causes the temperature to raise, which increases the amount of current that flows at a given applied float potential. That lowers the polarizations because as the temperature goes up, typically conductivities go down, kinetic overpotentials go down. And this can lead to a runaway process where lower polarizations lead to higher current, which causes more heat generation, which continually lowers the polarization. This is called thermal runaway. Define here the float voltage is the voltage at which a battery is maintained after being fully charged to maintain that capacity by compensating for the self-discharge of the battery. Okay, and the last topic I want to cover in this lecture is mechanical considerations for batteries. You could have volume changes. This is, of course, due to the intercalation in a lithium-ion battery. The negative electrode changes by up to 10% volume, maybe more in some modern carbon-silicon composite batteries. This is the negative electrode, is typically the carbon electrode. The positive electrode changes by about 2% volume. The components all expand and contract based on temperature, and this can lead to mechanical instability. So you need to control size and account for possible vibration or shock. Some compression is typically good inside of a battery to prevent delamination of all the electrodes and current collectors, but too much compression can cause breakdown of the separator. You can get shunting between the electrodes, so direct contact between the electrodes, and that will of course lead to thermal runaway and a dangerous result. So to end, I'll just review some mechanical engineering terms you might hear in the context of batteries. One of those is stress. This is the force across a small boundary per unit area of that boundary for all orientations of the boundary. So sigma, the stress, is defined as the force over the cross-sectional area of an interface between two objects. So you can see here, this is the intersection of these two spheres, a small area, and there's a force being applied, pressing the two spheres together. And the stress across the surface element, which is this yellow disk, is the force that the material on one side, this top ball, exerts on the material on the other side, the bottom ball, divided by that area of that yellow surface. So it's sort of like a pressure, but it's of two materials pushing on each other. So stress is something that's causing a material to potentially deform because of pressure, force over area. Strain, on the other hand, is a measure of the deformation representing the displacement between the particles in the body relative to a reference length. So if I have a rubber band and I have my fingers in that rubber band and I move my fingers apart and now I stretch that rubber band, the strain is just the change in length over the reference length, the initial length of my rubber band. You could imagine, for example, a rod, and if I bend that rod and make it into a circle, I am deforming it, and if I'm, in that case, not changing the overall length of rod, the distance between these two red dots, if I follow the length of the rod, then I'm actually not inducing any strain. Because in this particular case, it's bending, the displacements are associated with rigid translations and rotations of material elements, and there's not much displacement, as in the case of the rubber band, which I was actually pulling the two ends of the rubber band apart. Another term you'll hear is Young's modulus. Typically it's given as a pressure, and you get the Young's modulus from a stress-strain curve. So in a stress-strain curve, you apply a known stress and you measure the resulting change in some mechanical variable like the length of the system. And so the Young's modulus is just the slope of a stress-strain curve. It's how much strain, it's how much stress So something with a high Young's modulus requires a lot of stress to get a small amount of strain, where something like a rubber band with a low Young's modulus requires very little stress to get a very large strain. They call this linear regime. They call this initial part of the stress-strain curve the linear elasticity regime of a uniaxial deformation, so pulling in one direction, deforming in one direction, and watching the strain of the system change linearly with the applied stress. Where you start seeing a deviation from that is called the yield strength. So you might have a dramatic failure of your material, and therefore you get a lot of strain very rapidly before other processes start to come into play. For example, necking, strain hardening in metals, and eventually fracture, where the whole system breaks. And that's all I wanted to share with you today. I look forward to discussing some of this stuff with you in class soon.